Welcome back to College Algebra. Today we're going to be finishing up Chapter 6 with exponential and logarithmic equations. So this is kind of where all of this exponent and log chapter has been leading, solving equations or solving for x with exponential functions and logarithmic functions all in the same thing. So let's go ahead and get started. And as we finish the last, or one of the last chapters, Chapter 7 will be pretty short, and the last test you'll have to take, I feel like the verse of the day is pretty appropriate. It says, I fought the good fight, I've finished the course, and I've kept the faith. Well, that's not the verse, but that's a quote based on the 2 Timothy 4:7. And it's just an encouragement of Paul to Timothy saying, hey, you can fight the fight and keep the course and run the race of the faith that you've started. And while I'm encouraging you to keep the fight going against college algebra as you're working through these problems, the exhortation here is a bigger one, a call to faith that goes much farther than college algebra, but still applies to everything you do, being done with excellence and being done with integrity. And even though we're close to the end, I would encourage you and admonish you to do it well, to study hard, to plan well, so that you don't have to rely on things like photomath or mathway, but you know the material and you fought a good fight and you kept the faith and you finished your course. So as we approach the end, let's get started. So we're going to start this chapter with a one-to-one property of exponential functions. And it says that the only way for these two exponential functions to be true is if s and t are the same. And that kind of makes sense. If I wrote like 5 to the 1 equals 5 to the what, there's only one thing that makes that true. It would be 1. And so it's kind of a maybe obvious property, but one we can use to our advantage a lot. So for example, here's an equation, and using this property, we can say we know that 2x has to be equal to 3x plus 2. And so then we solve the equation like we've solved a lot of equations before. Move the 3x over and you get negative x on the left equals 2, which means x is equal to negative 2. We solved our equation. If you go back in and check your work, you could see that you would get 5, plug and chug it in, and you get 5 to the negative 4 over here, and negative 2 times 3 is negative 6, plus 2 is 5 to the negative 4 over here. And so it works out. Sometimes there's not as readily apparent of a base, but it's still there and it's hanging out. So the left side just looks like 5 to the 2x, and the right side is sneakily still a base 5. It just takes a little work to get there. And so what I'm going to do is I'm going to rewrite 25 as 5 to the second power raised to the 3x plus 2. And so what that means is we can use our exponential properties that says if you have an exponent outside of an exponent, you multiply them to get 5 to the 2x equals 5 to the 6x plus 4. And now we can apply this property of what's it called, one-to-one property of exponential functions to say now those 5's just disappear and we're left with 2x equals 6x plus 4. So if we solve that equation, we end up with subtracting the 6x and getting negative 4x equals 4, which means that at the end of the day, x equals negative 1. And you notice we're doing a lot less steps than we did at the very beginning of the year. As we approach this end of the year, we're kind of moving along through the algebra and just getting to the solutions. All right. This next one's actually taking it a step back. It's a little bit easier. 5 to the x equals, and you know that you can rewrite the square root as 5 to the 1/2. And so we're staring at our answer based on this one-to-one property, x equals 1/2. And last, a kind of tricky one. They're just trying to be a little sneaky here. There's no power of 2 that turns into negative 100. More so, if you try to think of a number up here that will turn into negative 100 or even a negative at all, you can't, because the graph of the exponential function was never negative. It always resulted in positive numbers. And so no solution is the only thing that could happen here. you could try for the rest of your life to figure out a number that goes into x right there, and it won't happen. There is no value and that can get plugged into that exponent that would result in a negative number. We're going to learn a tool in a second where you can see that really happen, where we apply the log to both sides, and you'll see that it's a domain error on the log. All right? So now we're going to solve some equations using logarithms. The first equation they give us, and the only equation, no, we'll get a couple more. Yep. The first equation they give us does not have the same basis. So we're going to have to use a log that we choose to solve this thing. There's no way to get 2 and 3 to have the same base, and so we're going to use logarithms to solve this equation. So what we're going to do is, just like we used to in the old days, what you do to one side, you're allowed to do to both sides. And we're going to take the natural log of both sides. So the natural log of 2x is equal to the natural log of 3x plus 1. And if you remember from our log properties, those exponents can do a really cool thing. We can move them to the front. So we have x times the natural log of 2 equals x plus 1 times the natural log of 3. And now it's just a matter of algebra to solve for x. Keeping in mind, a really key detail here is that the natural log of 2 and the natural log of 3, ln of 2 and ln of 3, are just numbers. They're not anything special. They're decimals that we don't know, so we're going to leave them alone and not make them decimals. But they're just numbers that we can distributive property, we can multiply, we can add, we can do whatever we want to with them, because it's just like it was a 2 or a 3. It's just a little bit uglier looking. So I'm going to start by distributing that natural log. I'm going to get x ln of 2 equals x ln of 3 plus 1 times the ln of 3 is just the ln of 3. And then I'm going to say, well, what if I got my x's on the same side? So x ln of 2 minus x ln of 3 is equal to ln of 3. And doing that short, small manipulation might have a couple of you thinking, oh, I think I know what I can do next. I see a common term or a common factor that I can factor out. And so if you factor out that x, you're left with ln of 2 minus ln of 3, and the x is on the outside. And so you've got one step left to get x completely by itself, and that's to divide by that big old parenthesis set. So I'm going to divide by the natural log of 2 minus the natural log of 3. And what you do to one side, you have to do to both sides. It'll cancel out on the left, and we'll be left with x is equal to the ln of 3 divided by the ln of 2 minus the ln of 3. And we're just going to leave it right there. All right. Do we know what the ln of 3 or the ln of 2 is? We don't. And so we're kind of just going to leave them alone and not try too hard to get a decimal that we don't know. So what happens if you have a coefficient in front? Well, this is just them trying to trick you into doing math from this section that you don't have to do, because you have old sections of math. You have like chapter 2 where you say, oh, I can divide 3 by both sides. Divide 3, and I'm left with e to the 0.5t equals 11 over 3. And now here's that trick that I was saying that we were going to get. And if we go back to the problem number 1 of the whole day, we could apply this trick to it and solve those problems really, really fast. But it's good to use the one-to-one property. So here's the trick. The way that we get rid of the e and the way that you get rid of any base is you log it with that base. And so if I want to get rid of this e, I'm going to natural log both sides. And what that does is it allows me to draw a line through the natural log of e and say all I'm left with on this side is 0.5t equals the ln of 11 over 3, and then you're home free like you're in section 2. So t equals the natural log of 11 over 3 over 0.5. Divide both sides by 0.5. And if you're thinking about, oh, dividing by 0.5 is the exact same thing as multiplying by 2, you'd be right. And so that's 2 times the natural log of 11 over 3 was your missing t value. So the trick here is to say, well, I've been in college algebra all semester. I have other algebra skills like that initial divide by 3 skill that I don't want to forget. Similarly, here's another college algebra skill that you don't want to forget. You can combine like terms. And so those two e terms, 3 equals, if you subtract e to the 2t from both sides, you get 6e to the 2t. And now you can solve it by dividing by 6. Dividing by 6, you get 1/2 equals e to the 2t. And the trick we just said to get rid of that base e was to take the natural log of both sides to cancel out the e. But what you do to one side, you have to do to the other. And so you're left with 2t equals the ln of 1/2. Last step, divide by 2, and you're left with t equals the natural log of 1/2 divided by 2. And so the skill to get rid of a base is to log it with the same base. When we move to logs, it's going to be really similar. The skill to get rid of a log is going to be to base it with the same base. All right, we've got one more type that is probably going to show up on your homework, so I think it's worth doing. And this is when a e to the x function actually has a different form. And so this function, they don't combine because they're not like terms. They don't have the exact same variable. And so I'm going to move all terms over to one side, set it equal to 0, and say that looks a whole lot like something else. That looks a whole lot like a quadratic from back in the day. And actually, using exponential properties, I can rewrite e to the 2x as e to the x to the 2 minus, and I'm putting parentheses around this e to the x so you can see something cool happen here, equals 0. I'm going to pick a letter, any letter in the world. I'll pick u, and I'll say, hey, I'm going to pick this letter u. I'm going to say for the rest of this problem, u equals e to the x. And so what I'm left with is u and u squared minus 2 equals 0. And that looks like a problem that we've done before. That's just u minus 2, u plus 1 equals 0, which means u equals 2 and u equals -1. But wait, u wasn't u in the first place. What was u actually? We're going to bring our u back into play now that we're down to our last step. And we're going to say u wasn't u was e to the x. And so e to the x equals 2, and e to the x equals -1. And how do you get rid of a base e? You natural log it. So the natural log of e to the x cancels out, but what you do to one side, you have to do to the other. And so we say x is equal to the natural log of 2. And we do the same thing over here where the natural log will cancel out that e. And so we're left with x equals the natural log. What you do to one side, you have to do to the other. The natural log of -1. Hold up. You're not allowed to have a -1 inside of a natural log. It's against the rules. You're not allowed to have any negative. You're not even allowed to have 0 inside of a log. That was from the domain restrictions of log. And so that's not a solution. And we're left with only one good solution. X equals the natural log of 2. All right. So that's solving exponential functions. When they have exponential functions and you're solving for x, that's a lot of the skills and tools to do it. Now, what happens if they start with a log? Here's what we're going to say. We're going to do our college algebra skills first, like we've been doing. So our college algebra skills would say, move that 6 over because we don't like it, and then the cool step's going to come in. All right. So when you had an exponential function, you logged it with the same base. When you have a log function, you base it with the same base. So what's the base of the natural log? The base of the natural log is e. And so what I'm going to do is I'm going to exponentiate the entire side. I'm going to say, hey, entire side, you're now an exponent to e. And a lot of times I'll do that little caret so you know it's an exponent and we're not just writing a random e. But what you do to one side, you have to do to the other. And that's going to cancel that whole e to the natural log and leave us with just x equals e to the 4. And so there's the skill to get rid of the natural log. So we learned that log is the skill to get rid of the base, and basing is the skill to get rid of the log. So we'll do another one that looks like it. Remember, don't forget your college algebra skills just because we're in logarithms. Your college algebra skills say divide by 2 first, and that's what we're going to do. So the natural log of x plus 1 equals 5. Do the easy algebra first. It'll make your logarithm way easier to solve. And how do you get rid of the natural log? You base e it. And what you do to one side, you have to do to the other. And so we're left with x plus 1 equals e to the 5, which means that x is equal to e to the 5 minus 1. All right. Logs have the same one-to-one property that logarithms have the same one-to-one property that exponential functions did a while ago. And so yes, you can use the one-to-one property, but now that you have this skill of exponential functions, I would probably just use that skill to get rid of these logarithms. And I would say raise both sides by a factor of e. And so now you've canceled out both natural logarithms, and you're left with x squared equals 1. And how do you solve that? Well, you square root both sides, and you get x equals the square root of 1. But since you introduced the square root to the problem, you have to introduce a plus or a minus. You undid a square, and so you introduce a plus or a minus. And so you're left with x equals 1 and x equals negative 1. Now pause. If we look up here, there's a strong note that says when solving logarithms, check to see if it's an extraneous solution. Just like with square roots, logarithms have domain restrictions, and so we need to make sure we're even allowed to do that thing in the first place. And so I'm going to check both terms, and I'm going to say the natural log of 1 squared equals the natural log of 1. Is that true? So that's just the natural log of 1 equals the natural log of 1. 0 equals 0. Check. That is true. Well, let's check the negative one, because a negative is a little scarier of an answer to have, especially when you're working with logs. Negative feels kind of scary. So the natural log of negative 1 squared equals the natural log of 1. Well, that's just the natural log of 1 equals the natural log of 1, and it checks out too, because that's 0 equals 0. So in fact, we do have two good solutions. We did need to check, but we ended up with two good solutions. And that was the last property of logarithms. I think since we introduced this rule, I want to go back up to the top and show you what I was talking about at the beginning. Here's try it 4. This is a great one to practice on. So now that you have this skill of getting rid of the base by logging it, what I'm going to do is I'm going to say, okay, we have a base of 2. This is just a different way to look at the same problem. How do we get rid of a base of 2? Well, I'm going to log with the base of 2 it. And what that's going to do is it's going to cancel the log, the 2, and the 2, and leave us with just an x. But what you do to one side, you have to do to the other. And so x is just equal to log base 2 of negative 100. And if you remember our talk about domain restrictions on the log, we said they were not allowed to have a negative. And so there is no solution. It does not exist. There's no solution to that problem. And we did that by using that cancel out property of the logarithm with the same base. And congratulations, you just finished section 6.6, which means you have a test on logarithms and exponentials coming up. I'd encourage you to go back and read through the notes that you might have sped through as we got towards the end of the semester. Practice the homework problems, practice any review problems you have, watch the videos again if you need to, and reach out to your instructor if you need help with anything. We'd be more than happy to help you as you master Chapter 6, Exponential Functions. Have a good day, and I'll see you next time.